Welcome to this yet another class on linear algebra through geometry. I am Dr. Arulalan Rajan, and I will be dealing with the vectors aspect of this course. In the previous weeks, you would have looked at solving systems of equations. You would have understood what is it to express a system of equations in the form of a matrix, finding out solutions for the system of linear equations, and so on. And we would have also seen a lot of visualization in terms of intersecting lines, intersecting planes, and non-intersecting lines, and so on. What we will do from now on is going to look at a slightly different picture of the system of equations itself, but we will go there after some time. But we are going to look at the idea of vectors, points on planes in spaces, vectors in spaces, and so on. We are going to look at that, and finally try to kind of look at bringing in the idea of vectors and then the idea of system of equations together, and then explore this domain of linear algebra in an even better manner. Again, as we told before, we will also have a lot of visualizations which we planned out for this course. So let us get going. So in this week we are going to look at the basic elements of geometry, which are basically points. Then we are going to look at vectors and a lot of other stuff. So let us get on. So let us begin with the idea of points. So what is a point? A point, we all know, it is the most basic entity of geometry, most basic geometric entity, which typically defines that indicates a particular location, that indicates or that is a particular location, in fact particular location in a coordinate system. So it is basically as I said, it is a location, and this location can change depending on the choice of the coordinate system, location in a coordinate system. Now, so what does it mean? A formal definition of point is basically a reference to a location. It is a reference to a location, right. For example, let us look at this. A point A, which is denoted as 3, 2, we mean the following. The following by saying A 3, 2 as, we will look at this. We are going to look at a coordinate system where I am going to have, let us say, an axis which is say E1, and I am going to have another axis E2. I am going to have 0, 0 there, and then I am going to mark all these points. So we are going to get this. So 1, 2, 3, 4, 5, etc. 1, 2, 3, 4, and by 3, 2 it is just going to mark that location, which is going to be 3 units along the x axis, and I mean E1 axis, and 2 units along the E2 axis. So what are we going to say? We say that the point A 3, 2 is basically 3 units along the E1 axis along the E1 axis, and 2 units excuse me, along the E2 axis. Now what does that mean? What does it actually indicate, or how are we going to generalize this? So in general, So, in general we have this representation, we have a point P which is having a in a 2 coordinate system, we have an ordered pair P1 P2 where P1 is the units along x axis or the E1 axis and P2 is the units along the E2 axis. Now, what is interesting is the coordinates P1 and P2, the coordinates P1 and P2 depend on the location of what we call as the origin, the location of the coordinate origin. It is very easy to understand that if we change the origin, then the coordinate changes, right. Let us look at a typical example. What is it to say that it is it depends on the location of the coordinate origin. So, what we do is for that we are going to look at let us say 3 different coordinate system here. Let me call this let me take this as the standard E1 E2 axis. I am going to mark 0 1 I mean 1 2 3 4 5 6 and so on. Let us say 1 2 3 4 5 6 1 2 3 4 5 and 6. Now, what we do is we are going to mark this point, let us say example. We will look at the same 3 2 as we had seen before. It is like it is going to be this point, this is going to be 3 2. Now, what I am going to do is I am going to change the coordinate system here, which means I am going to shift the origin. I am going to shift the origin to let us say a new origin. I am going to have a new coordinate system where in which I am going to have this. The origin is shifted to let us say the origin is shifted to 2 comma 3. This is my new origin. Let me call this as axis as E1 prime and that axis as say E2 prime, in which case the point 3 2 is going to be. So, I am going to have mark these points as like say 1 2 3 4. I am going to have this as 1 2 3 4. In the new coordinate system, which is basically 3 2 here, this point, the original point 3 2 which was there would actually correspond to 1 comma minus 1. Yeah. So, this would basically 1 unit along the minus 1 unit along the E2 prime axis and 1 unit along the E1 prime axis. So, this point would get translated to 1 minus 1 in E1 prime E2 prime coordinate system. That is exactly what we meant by saying if you choose the axis to, if you choose the coordinates to be different, we are going to have a different set of the point is going to change, right. Now, what is interesting is we see that the location of a point, as we mentioned earlier, the location of point is basically coordinate dependent, or the where you fix the origin, it is dependent on that. But now what we want to do is let us assume that I have a point here. Let us assume that I have a point in the same say E1 axis, E1 E2 standard representation where I have this 0 0. Let me again go back to my point which was like, okay, this is, let me take this point 2 3, let me have this point 2 3 and I want to move from this point 2 3 to another point in the say even in the coordinate system where let us say I am going to look at the point which is 4 comma 1, right. These two are two different points that I have, say I have this point to be let us say P and I have this point to be P, the point Q. The question is how do I move from 2 3 to 4 1, right. So how do we travel from, how do we move from 2 3 to 4 1. So how do we go about doing this? It is easy to see that okay. So the question is how do we move? If you look at the point 2 3, in order to go to 4 1, let us see if we can do this. 2 3 plus 2 minus 2 gives me 4 1, which means I have to travel 2 along the even axis here, 2 units along the even axis here. So I have to go like this, 2 along, this is this 2 units along the even axis, and then I have to travel minus 2 units along the z2 axis, which means I have to go from here to here. This is the path that I follow, and that path is basically given by this direction, and that quantity which we are going to have here, which is going to tell you the direction along which you have to move to go from 2 3 to 4 1 is what we call as a vector. We will call this as a vector V. Is this clear? So what we do to move from, let us say to move from 2 3 to 4 1, we move along the direction, we move along the direction of direction of 2 minus 2. Yeah, that means what we see is, that is, we have this point P whose coordinates are given by let us say P1 P2, which is equal to 2 3, and we want to move from here to this point which is Q, which is given by Q1 Q2 whose coordinates are 4 1. So what we do is we say P plus this V is going to give me that Q, which is basically the point 4 1. In what this implies that the vector V is basically given by the difference between the two locations Q minus P. Is that clear? So what we say is the vector V so what are we going to say? We are going to say that the point P1 P2 plus V1 V2 is going to give me coordinate wise addition. We are going to do component wise addition, P1 plus V1 P2 plus V2, and that is going to give me my new coordinate Q1 Q2, and that is precisely the destination that I have to go from the original source, which is P1 P2. So what we see is this V1 V2, which I will notate it as V, is basically a difference between 2 points, is a difference between 2 points, and what is interesting is it is not just difference between 2 points. What is interesting to see is it also describes a direction and and a distance, right, or a displacement. So we are going to say that which describes a direction, describing their direction and a distance. So which we together say okay, it is going to be some kind of displacement we are going to have, right. Now so what does it actually mean? what is it to say that I have this vector v1 v2. So, what does it actually mean? We should probably be able to understand it again through a lot of visualizations. So, let us probably look at this. So, what is it to say? The vector, or what do we mean by saying vector 2 minus 2? What do we mean by this vector 2 minus 2? So, let us look at let us again take the what would you call the help of visualization and see what it actually means. So, consider this. I am not even going to look at what kind of coordinate system or whatever. Let us take this, say 0, 1, 2, 3, 4. Let me mark these coordinates, say points E1, 1, 2. Let us try to look at this vector 2 minus 2. This is the vector v that we have, which is 2 minus 2. How does this look like? Say for example, let us take the initial point, let us take this initial point to be 2 comma 0 comma 2. Now, what we want? We want to go 2 minus 2. So, I have this is a 2 minus 2 vector. Now, what we do is again one more we can see, say I want to go from origin to 2 minus 2, this is the point that I want. So, that is a location. So, this is again 2 minus 2, then I can look at let us say I want to go from 4 3 this point. So, I will say 4 3 and I will go down to 2 minus 2. So, it is going to be 6 1. So, 6 comma 1 is here. So, you see that sorry, something interesting that happens 4 3 6 1, right. We see that almost all these vectors are all parallel to each other. That means irrespective of this location that we have, this vector v which is 2 minus 2 is something that you can see which is 2 minus 2, all these vectors that we see are 2 minus 2. What is it to say? You can have multiple number of 2 minus 2, this is what we are trying to say. So, we can have multiple vectors which correspond to this 2 minus 2. That means, this vector 2 minus 2 is independent of the coordinate, is independent of the coordinate. That is what we want to emphasize on. So, whenever you say a vector, the vectors, all the vectors that we have seen in the previous example are all 2 minus 2 vector, and it is irrespective of the coordinate. But what the difference that we see is the point, when we say the point 2 minus 2, that point is fixed, whereas the vector 2 minus 2 can be anywhere in the space. Is that clear? That is the basic difference that we have. So, we say that the point, if we denote the point P as 2 minus 2, the location is fixed, right, the location is fixed. However, the vector 2 minus 2 v which is equal to 2 minus 2 can be anywhere in the space, can be anywhere in the space. I hope we understand a clear distinction between a point and a vector. As we said earlier, a point is basically a location which is fixed, whereas a vector is going to be anywhere in the space. Is this clear? So, it is in fact it is this which is going to differentiate. So, this is the point of difference between or a vector and a point as such. Is that okay? So how do we, what do we conclude? We say that a vector has no fixed position spatially. The moment we say a point, the spatial location is fixed. Is that okay? Now, so why would we even want to look at the difference between a point and the vector? So let us look at this. So why study points and a vector? So what is the how do we differentiate once more? So let us do this. How do we differentiate a point and a vector? So how are we going to differentiate? We are going to say that points describe locations, and are coordinate dependent. This point has to be driven home because typically when we say a point, we make a very casual reference to points and stuff, and many times you also see people try to interchangeably use the idea of point and vectors. But here what we are going to say is points very specifically mean that they describe locations and are coordinate dependent, whereas our vectors are interesting fellows. Vectors are entities, vectors are coordinate independent entities. Now why are we trying to emphasize so much on this difference between the points and vectors? It is very interesting because when we try to make constructions, geometric constructions, we would want to make coordinate independent constructions rather than coordinate specific constructions, because when you work with points where the locations are fixed, you are going to have serious trouble, which we will see in a couple of minutes from now. So what we do is, what are the operations that we can do on a coordinate independent entity, and what are the operations that we can do on coordinate dependent entity. So that will tell us clearly like what is the difference it is going to make. So let us look at coordinate independent operations. That means it says that this is going to be an operation or set of operations that we are going to perform on vectors, or it could be a point and a vector, whereas whatever operations that you try to do on points, they will be coordinate specific. So these are typically using these are done on, let us say these are done on vectors, what do we mean by that? First of all, we must understand how to get a vector. So suppose I have a point P, and a point Q with coordinates, let us say P1, P2, and point coordinate of Q, which is Q1 and Q2, then we know that the vector V is given by Q minus P. That means you want to move from the point P to Q. So the direction is basically given by Q1 minus P1 and Q2 minus P2. That means we understand that if you actually subtract a point from another point, we get a vector. So we get a vector when you subtract one point from the other. The second thing that we will do is we understand that if we add or subtract two vectors, we will see what it means to add or subtract two vectors. Add or subtract 2 vectors, we get another vector. That is the most interesting thing that we can look at, we get another vector. Let us take a simple example again in terms of graphics and then see what it means, because this again has a very serious implication. We will look at it. So, let us consider again go back to our vector. So, consider let us consider this vector, let us say u, which is given by let us say 2 1, and let us take this vector v and let v be another vector which is given by minus 1 3, right, which means we already know that the vector 2 1 and minus 1 3 they have a direction. So, graphically how are we going to do it? Let us look at that, for which we are going to again draw our axis and try to understand from here. So, let us mark all our points 1 2 3 4 5 6. Now, let us first mark the point 2, the vector 2 1, the vector 2 1 is going to be here, this is the vector 2 1, and the vector minus 1 3 is going to be here, minus 1 3 is going to be here. Now, what we want is let us try to add these two in the plain way, where we are going to look at 2 1 plus minus 1 3. So, I am going to get 1 4, and 1 4 is basically this point that we have. So, how do we add these two vectors? All we need to do is we have learned from our school education and probably even undergraduate studies, where we know that if you want to add two vectors, you move the head of the tail of one of the vectors to the head of the other vector. So, what I am going to do is I am going to move this guy, the blue guy here, minus 1 3, this is again minus 1 3. So, the resultant that we get, here is basically the vector that we have. What is that vector? That is 1 comma 4. I could have as well moved this green vector to the tail of the green vector to the head of that vector, which is minus 1 3. This vector is minus 1 3, let us call this as the vector v. I could have as well moved that. If we move that, we would still get to the same point, which is 1 minus 4, I mean 1 4, right. Now, what I do is I will take the 2 1, instead of choosing it from this reference point wherever that I have had, which is 0 comma 0. Suppose if I take 2 1 from the point 4 comma 0. So, from the point 4 comma 0, if I take 2 comma 1, this is going to be this vector, which is let us say 6 comma 1, that is the green one, and I am going to get minus 1 3, 4 comma 0 minus 1 3 would basically be 3 comma 3. So, we are going to have 4 comma 0. So, 3 comma 3, let us look at that. 3 comma 3 is here. So, the vector is going to be here. Now, what am I going to do? I am going to again do the same business that I did. I move the tail of this vector, blue vector, to the head of the green vector. So, I am going to get here. So, I am going to do this with this reference. If I see, let us take minus 1 3, minus 1 3 will be 5 4. So, 5 4 is going to be this point. So, now we see that the resultant vector is going to be this, right. The same thing I can do with again. So, what we see here is that So, what we see here is independent of the location you get the same resultant. The vector, as we said, you are going to have the vectors to be the same vector to be available in the space like at different locations. It is basically as we defined the vector to be spatially what do you call we just had the previous definition where we said a vector has no fixed position spatially, and that is exactly what we see here. If we change the vector just a minute. So, all we do is these two vectors are the same, they are basically the same vectors that you have. Again these two guys are the same, these two guys are the same. So, you could see that you can move around when you have your vectors, whereas you cannot do that when you have points. Is that clear? So, adding or so let us do this. So, in fact we could in the previous figures we could see that the resultant of two vectors, the resultant of let us say u and v, which is given by u plus v, is actually the diagonal of a parallelogram formed by diagonal of a parallelogram formed by the two vectors, the vectors u and v, right. Good. Now, we already saw that the next operation that we see is adding a vector to a point yields another point, adding a vector to a point yields another point. Results in another point. The fourth operation that we are trying to look at is basically scaling a vector. Scaling a vector, we can actually do the scaling by a constant k. So, what is it to say scaling a vector by a constant k? I am going to multiply k times this vector v, which is nothing but k into v1 v2, and this k is going to multiply each of those components. So, I am going to get k v1 k v2, which is yet another vector. This is another vector. So, scaling a vector yields another vector, right. Basically the scaling adjusts the length of a vector. Is that okay? So, scaling typically adjusts the length of the vector, and what is interesting is we just need to know what happens if k is positive. If k is 0, then the direction of the vector remains the same, If k is less than 0, the direction of the vector reverses, the direction is reversed. And interestingly, we will see that if k is equal to 0, we end up getting the 0 vector with both the components to be 0 comma 0, 0 vector 0 comma 0, right. However, this is with respect to the vectors. suppose if you look at coordinate dependent operations, that means I am going to do operations on points. So, let us look at that coordinate dependent operations. In order to understand this, what we do is we will basically look at a single axis system rather than looking at two axis, because it will be easy for us to understand from a single axis point of view and then go ahead with multiple axis or two axis system. So, for that what we do is we will look at a single axis system where we are going to look at addition of points, scaling of points. Let us see what it means and let us see what makes this a completely different operation compared to what we did with vectors. Okay. So, for that let us look at this. So, let me do this for some reason. Let me have this, let me call this blue line as my single axis E1, where I mark all the points 0, 1, 2, 3, 4 and 5. Let me mark -1, -2, -3, -4. Now, what I do is I also take another axis where I shift the origin compared to this. Let me assume that this is the our usual or let us not call this as usual system. Let us say that this is the reference system that I have. So, this is my reference axis. Let me have this shifted axis where I am going to do a shift by 2. So, my origin is going to be here in this case. This is going to be 1, 2, 3, 4. This is -1, this is -2, this is -3, this is -4, -5, -6. So, this is going to be my E1 prime axis, which is going to be shifted from the reference axis, shift by 2, and let me have one more axis where in which I am going to have this, where I am going to shift my reference or shift my origin to let us say -1. So, my origin is going to be shifted to -1. So, this is going to be 0, this is going to be 1, this is going to be 2, 3, 4 and 5. Let me call this as E1 double prime axis. This is going to be -1, this is going to be -2, this is -3, -4 and -5, right. So, what am I going to do here? Now, let me take a simple example where I am going to add 1 and I am going to add it with 2. That is exactly what we say addition of points. We take the point P and then we add the point Q. Here P just has one coordinate which is equal to 1 and Q has just one coordinate which is equal to 2, right. So, I am going to add this 1 plus 2 and I am going to a destination which is basically my value 3. Equivalently, if I look at the red system, the corresponding point, the point corresponding to P is equal to 1 is basically -1 here, and the corresponding point Q is equal to 2 corresponds to Q is equal to 0 in the E1 prime axis. So, what am I going to do if I add these two guys, if I add these two guys, I again go back to -1, and let us look at the same thing here. If I were to add this 0 and 1, because that is exactly what I am going to add here, 1 plus 2. So, what do I go here? I basically go from So, I am going to add 0 plus 1 and I will remain at 1. Is that clear? Now, you see it is the same operation that we are doing, but with different coordinate system the value that we get is different. So, what we are going to say is this coordinate dependent operations, this is basically addition of points is not well defined. Addition of points not well defined. Yeah, okay. Now let us see if the scaling makes sense, because we did vector scaling there. So we want to look at if scaling actually makes sense. So let us look at scaling, right, where we multiplied by a scaling factor k. We will use the same convention that we had here, where we have this E1 axis. I will take 0, 1, 2, 3, 4, minus 1, minus 2, minus 2, minus 3, minus 4. Let me call this as the reference axis again. I will choose the same thing like red another axis where I have shifted it by 2 units. The origin gets shifted by 2 units. Let me call this as E1 prime. So the origin is now at this one, this is 0, this is 1, this is 2, and so on. This is going to be minus 1, this is minus 2, minus 3, minus 4, minus 5, and so on. And I am going to have my green, where in which the axis is right shifted by 1. So my origin is basically right shifted by 1. So I am going to have E1 double prime, where the 1 is basically here, origin is here, which is sorry, left shifted by 1. So the origin is basically here, the origin is basically here, it is at minus 1, the origin is here 0, this is 1, 2, 3, 4, 5, this is minus 1, this is minus 2. Now what are we trying to do? Let us say I will take this point 1, which is here. Let me take this point 1 and multiply it by 2. If I multiply it by 2, I go here 1 into 2, the scaling factor that I use is 2 here. So k, scaling factor k is equal to 2. I go here, this 1 was corresponding to minus 1 in this coordinate system. If I multiply it by 2, I will go to minus 2 here, and this 1 was corresponding to 2 in this coordinate system. I multiply it by 2 and I go to this, the point 4, which means even here we see that across the different coordinate system, the destination that you actually reach, or the result of scaling, does not seem to be the same, they are different. So even here we say that scaling is also not well defined. Now if this happens in just say a single axis system, I am quite sure we will be able to understand what happens if we look at a 2 axis system, where in which the axis get the coordinates are the origin gets shifted. So let us take another example in this case and see how it works. So let us look at our 2 axis system with E1 and E1 axis and E2 axis. So what are we going to do? Let us take the same whatever that we did before. I am going to look at this blue. The blue axis is going to be my this is my reference axis. This I am going to call this as E1 and E2. So I have this point 0, this is 1, 2, and so on. So the point, let us look at this. Let us just try to mark this point 1 comma 1 in this system. 1 comma 1 is this particular point that we see here. Now what I do, I am going to construct a new coordinate system, where in which the origin of this new coordinate system is going to be located as 2 comma 2. This is going to be my origin in the 2 comma 2 system, I mean in this new coordinate system, which I am going to call it as E1 prime and let us say E2 prime. So, this is going to be 0, 1, 2, 3, 4, etc. This is 1, that is 2, 3, 4, etc. Now, what we see is, and this is going to be minus 1, here it is going to be minus 1 and so on. What we see interestingly, the coordinate the point P is equal to 1 comma 1, the point P which was 1 comma 1 is equal to or is basically let us say in E1 E2 axis, in E1 E2 system corresponds to the point let us say P prime which is minus 1 comma minus 1 in E1 prime E2 prime system. Let us look at one more where I am going to define my new coordinate system, which is going to be here. Let us look at it in terms of green line. So, I am going to have this is going to be, let me take this to be my green coordinate system, where the origin corresponds to let us say minus 1 comma minus 1 in this system. Minus 1 comma minus 1 of my blue system, blue coordinate system is going to correspond to the origin here. So, this is going to be 0 comma 0, and it is interesting to see that the same point P which was here 1 comma 1 in this system, it would correspond to 1, 2, 3, 4. Let us take this as 1, 2, 3, 4. We see that the point 1 comma 1 here, it corresponds to what is that? It corresponds to 2 comma 2, right. This point is P double prime of 2 comma 2 in E1 double prime E2 double prime system. Let me call this as E1 double prime, let me call that as E2 double prime. Yeah, that does that I mean does that help us understand that what happens if you shift the coordinate system, the relative position of the point changes, and therefore, if you try to do any kind of operation on this, again say in terms of scaling, in terms of addition, in terms of adding 2 points, in terms of scaling a point, you are going to get different values. Is that clear? We could probably even say that we have seen that since the locations are going to be different, in each case whether you whenever you add another point and whenever you try to scale, things are going to be different. So, we will say that the coordinate dependent, so coordinate dependent operations not well defined, because as I said the locations keep changing, and therefore, we say that these are not well defined operations. Is that clear? So, to summarize what we have seen in this lecture, we understood the notion of a point and a vector, a point basically being the basic geometric entity. It has a fixed location, it is a fixed location entity. I mean fixed location here corresponds to the spatial location. Then notion of a vector, this is not a fixed, this is not spatially fixed. Whatever operations that we try to do on a vector, these are basically what we call as coordinate independent operations. wherein which we did vector addition and scalar and scaling basically, and in fact prior to that we looked at the idea of vector as a displacement with, it is an idea of displacement. That means if you want to go from which is defined by a direction and length, whereas this, as I said, it is a fixed frame of reference. So we also studied how things change, like when you look at the operations that you do on points. These are basically coordinate dependent operations. So we said that if you want to move from a point to another point, you follow the direction of a vector which has some displacement and which has a direction. So the question is, how do we measure the distance? That means, how are we going to measure the length of the vector, and we will look at that in the next lecture. Thank you.